Hey everyone, Hihu here from LeetCode. Today we're solving LeetCode 283. Move zeros. This is an easy problem. It comes under arrays and two pointers in the LeetCode 75 study plan. At first glance, this problem looks very simple. Just move all the zeros to the end. Sounds easy, right? But there's one important condition. We have to do it in place. That single requirement completely changes how we think about the solution. Let's first understand exactly what the interviewer is asking us to do. Let's understand the problem statement. We're given an integer array. Some elements are 0. Some elements are non-zero. Our task is to move every 0 to the end of the array. But here's the important part. The relative order of every non-zero element must remain exactly the same. That means we're not allowed to rearrange the non-zero values. We're only moving the zeros. There's another requirement. We have to perform this operation in place. In other words, we cannot create another array to store the answer. We have to modify the original array itself. So this problem isn't about sorting. It isn't about finding anything. It's about rearranging the existing array as efficiently as possible. Now let's see what that actually means using the examples. Let's look at the first example. The array is 0, 1, 0, 3, 12. Our goal is to move every 0 to the end. The expected output is 1, 3, 12, 0, 0. Notice something important. The numbers 1, 3, and 12 appear in exactly the same order. We didn't change their order. We simply removed the zeros from between them. Then pushed those zeros to the end. That's the key requirement. We're preserving the order of every non-zero value. Now let's look at another example. The array is 0, there's only one element. It's already a 0, so nothing changes. The output is still 0. Let's think about one more situation. Suppose the array is 1, 2, 3. There are no zeros at all. What should happen? Nothing. The array should remain exactly the same. These examples teach us two important things. First, we only move zeros. Second, every non-zero value must stay in the same relative order. Now the next question is, how would we actually solve this problem? Let's begin with the simplest idea. Whenever I solve a problem, I like to ignore the constraints first. Let's do the same here. Suppose the interviewer didn't say, in place. What would be the easiest solution? Most people would probably create another array. As we scan through the original array, we simply copy every non-zero value into the new array. Once we've copied all the useful values, we fill the remaining positions with zeros. Finally, we copy everything back into the original array. It's a very natural approach. It's easy to understand. And more importantly, it gives us the correct answer. So before worrying about optimization, let's first see how this brute force solution looks in code. Let's translate that idea into code. First, we create another list. This list will store every non-zero value we find. Next, we scan the original array from left to right. For every element, we ask one simple question. Is this element 0? If the answer is no, we add it to our list. If it's 0, we simply skip it. By the time we finish this pass, our list contains every non-zero element. And they're still in the correct order. Now comes the second step. We start filling the original array again. Beginning from index 0, we copy every value from our list back into the array. At this point, all the useful values are back in their correct positions. But there are still some positions left. Those positions should all become 0. So we simply fill every remaining position with zeros. And that's the complete brute force solution. It's simple. It's easy to understand. And it produces the correct answer. Now let's verify it using a dry run. Let's use the first example. The array is 0, 1, 0, 3, 12 initially. Our temporary list is empty. We start scanning from left to right. The first element is 0. Since it's a 0, we skip it. The temporary list is still empty. Now we move to the next element. It's 1. This is a non-zero value. So we copy it into our temporary list. The temporary list becomes 1 and next, we read 0 again, it's a 0. So we ignore it. The temporary list doesn't change. Now we reach 3, it's a non-zero value. So we copy it. The temporary list becomes 1, 3 finally, we read a 12, it's also a non-zero value. So we copy it as well. Now the temporary list contains 1, 3, 12. We've finished scanning the array. Now it's time to rebuild the original array. We start writing from index 0. Place 1 at index 0. Place 3 at index 1. Place 12 at index 2. We've copied every non-zero value. There are still 2 positions left, index 3 and index 4. We fill both of them with zeros. The final array becomes 1, 3, 12, 0, 0. That's exactly the output we expected. So the brute force solution works correctly. Now let's analyze the complexity. During the first pass, we scan the entire array to collect every non-zero value. During the second pass, we copy those values back into the original array. Finally, we fill the remaining positions with zeros. Even though there are multiple passes, each element is processed only a constant number of times. So the overall time complexity is O of n. Now let's talk about space. We created another list to store every non-zero value. In the worst case, the array might not contain any zeros. That means our temporary list could become as large as the original array itself. So the extra space required is O of n. The solution is correct. But there's one problem. The interviewer specifically asked us to solve it in place. We're still using another array. Can we get rid of it completely? Let's think about that. Before writing another line of code, let's stop and think. What are we actually trying to preserve? Is it the zeros? Not really. The zeros don't have any special order. They all look exactly the same. The only values we actually care about are the non-zero values. Those are the values whose order must never change. That's a very important observation. Once every non-zero value reaches its correct position, where will the zeros go? They'll automatically end up in the remaining positions. We don't need to move the zeros one by one. We only need to place the useful values correctly. That's the breakthrough. Once we realize this, the optimal solution becomes much simpler. Instead of thinking about moving zeros, we'll think about placing non-zero values. And that naturally leads us to a very common interview pattern. This problem introduces one of the most useful interview patterns: the read pointer and write pointer pattern. The idea is surprisingly simple. Instead of giving one pointer multiple responsibilities, we divide the work. One pointer is responsible only for reading. The other pointer is responsible only for writing. Let's understand what each pointer does. The read pointer scans every element in the array. It never changes the array. Its only job is to discover useful values. The write pointer has a different responsibility. It remembers where the next non-zero value should be placed. Notice how each pointer has only one job. The read pointer asks, "What value am I looking at?" The write pointer asks, "Where should this value go?" Separating these two responsibilities makes the algorithm much easier to understand. And this pattern isn't useful only for this problem. You'll see it again in many array problems, string problems, and in place modification questions. Whenever a problem asks you to process data, while writing the answer back into the same array, think about using a read pointer and a write pointer. Now let's build the optimal solution. Since we only care about placing non-zero values correctly, our read pointer will scan every element. Whenever it finds a non-zero value, our write pointer already knows where that value belongs. So instead of storing the value somewhere else, we simply place it directly into its correct position. Then, the write pointer moves forward, ready for the next non-zero value. If the read pointer finds a 0, nothing happens. We simply continue scanning. Think about what's happening. Every useful value slowly moves toward the front. The zeros are never pushed directly. They're simply left behind. And as more non-zero values move forward, the zeros naturally collect at the end. That's why this solution works without creating another array. Now let's see how we implement it. Let's translate this idea into code. We begin by creating a variable called write. Initially, it points to index 0. Next, we use another variable called read. This pointer visits every element in the array, one by one. Now comes the important part. Whenever the element at the read pointer is not 0, we swap it with the element at the write pointer. Why do we swap? Because the write pointer always points to the position where the next non-zero value belongs. Once the swap is complete, we move the write pointer forward. It's now ready for the next useful value. If the read pointer finds a 0, we don't do anything. The read pointer simply moves to the next element. The write pointer stays exactly where it is, because we're still waiting for the next non-zero value. And that's the complete implementation. The code is actually very small. The difficult part was discovering the idea behind it. Now let's see this algorithm in action. Let's use the same example one last time. The array is 0, 1, 0, 3, 12 initially. Both pointers start at index 0. The read pointer is looking at 0. The write pointer is also at index 0. Now let's ask ourselves a question. Should this 0 be moved to the front? No. We don't care about zeros. So the read pointer simply moves forward. The write pointer stays exactly where it is. Now the read pointer reaches 1 this time. We've found a useful value. Where should this one go? The write pointer is pointing at index 0. That's exactly where the first non-zero value belongs. So we swap the values at read and write. The array now becomes 1, 0, 0, 3, 12. We've successfully placed our first non-zero value. Now both pointers move forward. The write pointer is now at index 1. The read pointer moves to index 2. The read pointer sees 0. Should we move it? No. So only the read pointer moves. The write pointer stays where it is. It's still waiting for the next non-zero value. Now the read pointer reaches 3. Where should 3 go? The write pointer is pointing at index 1. That's exactly where the next non-zero value belongs. So we swap them. The array becomes 1, 3, 0, 0, 12 again. Both pointers move forward. The write pointer is now at index 2. The read pointer reaches the last element. It's the 12. Where should 12 go? Immediately after 3. The write pointer is already pointing there. So we swap the values. Now the array becomes 1, 3, 12 or 0. The read pointer has reached the end of the array. We're done. Notice something interesting. We never searched backwards. We never created another array. The read pointer simply discovered useful values. The write pointer placed them in the correct position. And the zeros naturally collected at the end. That's the beauty of this approach. Now let's analyze the optimal solution. The read pointer visits every element exactly once. The write pointer only moves forward. No element is processed more than a constant number of times. So the overall time complexity is O of n. Now let's talk about space. Did we create another array? No. Did we create another list? Again, no. We only used 2 integer variables. The read pointer and the write pointer. So the extra space required is O of 1. This is exactly what the interviewer was expecting. We've improved the space complexity from O of n to O of 1 without increasing the running time. Interview tip. Whenever you hear the words, modify the array in place, don't start coding immediately. Pause for a second. Ask yourself, do I really need another array? Very often, the answer is no. Instead, think about separating the work. One pointer can focus on reading. The other can focus on writing. That single question can lead you directly to the optimal solution. This is one of those interview habits that becomes useful far beyond this single problem. Let's quickly recap. Today we learned the read pointer and write pointer pattern. One pointer scans the array and discovers useful values. The other pointer remembers where those values belong. By separating reading from writing, we were able to solve the problem using only constant extra space. Whenever you see an interview question that asks you to modify an array in place, this is definitely a pattern worth remembering. And that's how we solve LeetCode 283. Move zeros. If you found this explanation helpful, make sure to like the video and subscribe to LeetCode. Thanks for watching. This is Huwu, signing off. Keep practicing. And I'll see you in the next one.